All right, so with this, we'll go over it fairly quickly here. We start off with some essentially definitions, major terms here. So knowing the three definitions of how we define an acid versus a base in each of these cases. Arrhenius said an acid had to have an H, had to have an H plus. A base had to have OH minus. Okay, very limited things to be classified as an acid or a base in this definition. Bronsted-Lowry, whereas the main majority of our information comes from and we use, an acid is an H plus donor, a base is an H plus acceptor. A lot more things could be classified as an acid or base here. And then our final part of the chapter talked about a Lewis acid and base. Lewis acid is an electron pair acceptor. Lewis base is an electron pair donor. All right. Know those, be able to identify those, and then be able to identify strong acids and strong bases. You essentially have to memorize that list that was provided to you in notes, and know this, that if we have a strong acid, and let's use hydrochloric acid, a major thing with hydrochloric acid, when it's dissolved in that water, it completely dissociates, which means it's going to break into our H plus and Cl minus. 100% of the H's are going to break apart from 100% of the Cl's. A major thing here with a strong acid is that we have one arrow, one direction. Whereas a weak acid, and I'm just going to put generic weak acid HA, we combine that with water H2O, and this is at equilibrium because only some of the H's from the weak acid break apart. Okay, strong, complete one-sided arrow, weak, equilibrium, you have reactions occurring in the forward and reverse directions. Questions over any of these five? Okay, fairly simple, multiple choice types of questions here come off of these, but any questions or anybody still need it? All right, so moving on with this. If I give you a Ka, know that the larger the Ka is, the stronger that is. So if we had weak acids, let's say, and I had one Ka of 1.2 times 10 to the negative second versus a Ka of 6.7 times 10 to the negative 12, that first acid, because it's closer to what we call, or what would be zero, there would be 0.021 in that first example, and then the other example would have 11 zeros, so 0.1167. That first example, the larger Ka is associated with the stronger weak acid. Same thing can be said about base values. Okay, be able to identify the strong or weak portion given the Ka or Kb values. We've already talked about this. The middle point here, chemical equation for a weak acid, weak base, equilibrium expression, two-sided arrows. That's pretty substantial here. Weak acids and their conjugate bases, all right, or weak bases and their conjugate acids, vice versa, right? So know that in our definition, we use that Arrhenius definition, or use the Bronsted-Lowry, know that a weak acid loses the H, that conjugate base gains that H. It's the only difference. Whereas a base, they start out without the H, they gain it, and that conjugate acid is the one with that extra H. pH and POH of a strong acid or base. simply plug that into the pH formula. Okay, so I say, hey, this is 0.1 molar solution of HCl. What's the pH? It's strong. You plug it into the pH formula. What I may do though is I may say, all right, this is the H plus value, or this is the concentration. Tell me what the POH. So you may have to go, oh, found pH, 14 minus that number gets me the POH. Okay, so I may have you flip around, just be careful on that. Those problems and exercises are pretty good. Questions? Anybody need this? All right, so going through this, if you're given Ka, be able to find Kb. You're given Kb, find Ka through this Kw equation. Now, your AP exam study guide, or your AP exam packet that I give you, has quite a bit of this info already embedded under the equilibrium section. It's pretty helpful to take a look at this, okay? This one at the top is our last one that's our multiple choice concentrated. These last 5 bullets, these are going to be where your fill in the blank comes from, okay? If I give you the hydronium H plus concentration, we need to be able to determine the POH. So in this case, you would first find pH via pH equals negative log of that concentration. Then you would take 14 minus that number to get to your POH. Okay? Questions on that type of question? These examples from those exercises packets work out really well. Next one here, if you are given the POH value, determine the hydronium ion concentration. So number 1, you're going to have to convert POH back to pH and then use that formula, pH equals negative log of our H plus, to figure out what is the H plus. So I'm getting you in these 2 problems, the fill in the blank, you go plug it into the pH formula, flip-flop some values around to get to that desired value, and then get to your answer. So you'll have to do multiple things. They're fairly simple multiple things. Questions? Anybody need any of this? All right, last 3 things. Notice on our last 3 things. 1, I'm going to keep it fairly simple. Everything's weak acid. All right. So for your test, everything will be a weak acid. Just know weak base could apply as well. But take a look here. All 3 of these problems, all 3 of your final fill in the blank involve ice charts. So number 1, it says you need to use the ice charts to determine the hydronium ion concentration and determine the percent ionization. So let's say, for example here, you are given some generic weak acid, and I'm just going to call my weak acid HA, and it's weak, so we have H2O. We're at equilibrium. That H gets donated. We form H3O plus Ra minus. What you're going to have to do in this is you are initially going to have to set up your ice chart, and you're going to be given some initial concentration. Let's just say hypothetically that your initial original concentration of the weak acid, let's just say, for example, is 0.02 molar. All right, just for example. I don't know what it's going to be on the test. You're going to take your initial value, right? And that's the only thing that you're given, which means we don't know this, we don't know that. Now, we're going to have to use our x's because we don't know what changes. So we would minus x, we would plus x on the H3O plus x on the H3O plus. You'd get down to equilibrium, 0.02 molar minus x, and x. Now, from here, You either have to look up the Ka, or I'm going to most likely give that to you. What you would do is this. You would say, hey, Ka is equal to x squared over that original concentration. And we're going to assume on this entire test that our assumption works. Okay, it's going to save you some time. Now, X is the amount of H3O or hydronium ion concentration at equilibrium. And so your final step, once you found X via your ice chart, what you're going to have to do is look at percent ionization. So you're going to take that X value that you found, the concentration of H3O plus, and you're going to divide it by your original concentration, which I just made up hypothetically at 0.02 molar. And then you'll multiply by 100, and that would be your final answer. Okay? Questions? Next ice chart, we want to find the pH. So what value in our ice chart are we going to have to use or have to find to get to our pH?
H3O.
H3O plus, perfect, right? So if we just generically set this up again, HA plus H2O, we say, hey, let's go to equilibrium. H3O plus RA minus. It's going to look really, really similar here. Oh, I take this back. I jumped one ahead. But this is going to look really, really similar to this. I just need to make one minor correction. One, again, we're given an initial value, original concentration. Let's just say for simplicity that this is going to stay at 0.02. I don't know what it's going to be on the test. That initial value is going to be given, and that's where you'll insert it in here. Again, this is made up, that 0.02, okay? You wouldn't have any whoop, I'm jumping ahead. You wouldn't have anything listed out for H3O plus or A minus. However, what you could do is this. If you are given the pH, all right, if you're given the pH, you can use the formula pH equals negative log of our H3O plus. Once you find the value of the H3O plus, you can plug that number in. So you'd solve it, you'd say, hey, H3O plus equals some number. I don't know what it is. You would say, okay, this is that value at equilibrium. Well, initially you started out with 0, so you had to gain that same number. And we could say the exact same thing from this. So we would have two of the same values coming from just the pH, and then you'd have to subtract that number from our HA value, okay? And so you'd get the number 0.02, whatever the case the original calculation is, minus that number, probably going to be a pretty small change. And our final answer would be this. You're solving for that Ka. So you'd plug all of those numbers back in to your Ka equilibrium equation, and you, in this case, would solve for Ka. Okay? Questions? Last problem still involves an ice chart here. We need to determine the pH. So this is where I was jumping ahead. Okay? Again, what was said that we had to find the pH?
H3O plus.
H3O plus. So it's going to look very, very similar to the first problem up top here. We can write it down just to show you again. But you are needing that H3O plus to solve and plug in into the pH formula. So again, just an example. Let's say we have HA, some generic weak acid, plus our H2O. We go to equilibrium. We get H3O plus, which is our item of interest, plus our A minus. All right. Now, for our purposes, again, we are going to need an ice chart. let's say, for example, the weak acid concentration, let's just keep it consistent. For our example, let's say 0.02 again. You would plug that value 0.02, 0, 0, lose some X, gain some X, gain some X. Our assumption's going to work, so we really don't need to worry about this minus X, but I'll just show it to you. And then at the end of the day here, you're going to do two final things. One, you're going to plug all of that into our formula. Ka, which will be known, will be given, equals X squared all over whatever that original concentration is. Again, 0.02 is just my hypothetical, what I'm using today. X is going to equal concentration of H3O plus. So your final step in all of this to solve the problem would be to say, all right, to find the pH, we need to put all of that into our H3O plus formula. All right. Questions? All right. Hopefully this gives you a pretty decent understanding about what's going to be on the acid-base part 1 exam.